Today we're going to do three more mirror cases. The first two involving concave mirrors. And once again, a concave mirror means the mirror is just like a plain mirror. It's silvered in the back, but it kind of looks like you're walking into a cave. You're walking into the depression area. And concave means you're reflecting off the front. Now the center of curvature, that means any point from the center to that concave mirror is going to hit at right angles. We talked about a point source of light means that you have light emitting in basically three dimensions, all possible ways. Any one of which could be filtered to, say, be a flashlight just going in one particular direction. So if we have one ray of light that hits parallel, notice that it reflects around the normal line, just like it was hitting a plane mirror. But also notice that it reflected back through the focal point. And we said that if you had a ray of light that went through the center, it would go back on itself, and those 2 points created an image, and the one that went through the focal point came back parallel. So all three of our light rays that we normally use to create an image show the image, and this was just a review. We said this was the positive side of a mirror, and the negative side would be behind the mirror, where if you had an image showing up behind, which we don't in this case, then that would have been virtual. But we said that that case was real, it was smaller and inverted. So now we're going to move on to a slightly different case, and we're again going to use the three light rays, the parallel light ray. That's the light ray that emits parallel to the center line of the mirror. And we're going to use the focal ray, that's the ray of light that goes through the focal point, and the center ray, the ray that goes through the center. Now we could use any ray we wanted to, but we'd have to get into some complicated math if we chose something else. So here I took the parallel ray, and just as our rule says, I've reflected it down through the focal point. And then this is just showing all the different possible rays that exist. But the one that goes down through the focal point would emerge parallel. And where any two rays cross, that is where your image is going to be. So the image is actually going to be way down here. Now the ray that leaves the candle that went through the center would never hit the mirror. But a ray that looks like it came from the center would reflect back on itself and go through the center and also go to that same point. So any two of those three would establish an image. And so this is also real. It's larger and it's upside down or inverted. So we'll do a little bit of the mirror math on this. If C is 20 centimeters and the image is 37 centimeters from the mirror, which seems about right, how far away is the object? So we're going to use the first equation, the lens maker's equation. And remember that F is half of what C is. So in this case, we'll say 1 over 10 for the focal point equals 1 over the image distance, which in this case was 37, plus 1 over the object distance, which is what we're looking for. And so we're just going to say 1 over D0 equals 1 over 10 minus 1 over 37. And we come up with an object distance of 13.7 centimeters. And that makes sense. Just does this line seem like it's, basically just under half of that line? Yeah, so it makes sense. Okay, in the next case, note that we've moved the candle even closer to the mirror. So we're once again going to find the image of the candle, and we're going to use P, F, and C. And the first thing we notice is that the parallel ray, not that we notice, but the parallel ray has to come back through the focal point, as always. Now, the ray of light that leaves the candle towards the focus point would never actually hit the mirror. So once again, we have to say the ray of light that came as if it was coming from the focal point would hit the mirror and reflect parallel. So where do they cross? The problem is those are diverging light rays. They keep getting further from each other towards infinity. They never cross in real territory, but they do cross behind the mirror. Notice I'm using dotted lines. That's because they cross back here and they're going to create a virtual image. So I'm going to try to draw that image with dotted lines because that is virtual. And that's because that's on the negative side. Okay, so that's like how a plane mirror works. We have the positive side and the negative side of the mirror. And if we wanted to look at the third ray, which would be the one that looked like it came from the center, that would also cross in back of the mirror at the same spot. So once again, of the P, F, and the C, you could pick 2 out of 3 to determine the image. And it's virtual, larger, and upright. So if the candle is 8 centimeters, that's the object distance from the mirror, and the image is 13 centimeters from the mirror, what is the center of curvature? So we're going to use 1 over F, and it's 1 over di plus 1 over do. But when we do 1 over the object distance, it's 1 over 8. And when we do 1 over the image distance, it's 1 over negative 13. Because, and I'm using negative because the image is on the negative side of the mirror. That's an important distinction. And I come out with F as 20.8, and of course I have to double that to get to the center point, which is 41.6 centimeters. Does that make sense? If this is 41, yes. Okay, so the convex mirror case, this is a little bit different. This doesn't look like you're walking into a cave. It's obviously the opposite of that. So in the convex situation, we once again are going to use P, F, and C, our parallel, focal, and center ray. So our parallel ray will hit the mirror and will reflect not through the focal point, but as if it came from the focal point. So it's going to deflect off in this direction. Now, the one that goes towards the focal point will obviously never get there because the focal point is behind the lens. But it's going to reflect parallel. Because remember, there's that kind of that inverse relationship between the parallel ray and the focal ray. And where those two diverging rays crossed will be, once again, behind the mirror. So if we extend the parallel line behind, I'll use a different color here, we'll see where these two rays cross, you get an image. You get a fake image or a virtual image. You think you see the candle there, but the actual rays of light have diverged. So it's a virtual image. And the third ray would be the center line. So the one that goes through the center line would just kind of reflect back straight, but that center point would also meet at the same spot. So once again, any two of those three will determine where the image is. All three of those rays were diverging. So we do have a virtual, and it's a smaller image, and it's clearly upright. So let's just do the mirror math on this. Actually, before we do the mirror math, I just want to point out that the side view mirror on your car is a convex mirror. Notice the object distance is greater than the image distance, which is why this note often is on your side mirror. Objects in the mirror are closer than they appear. So in this case, the candle is 40 centimeters from the mirror, and the focal distance is 15 centimeters. So where is the image? And then what is the magnification of this mirror? Keep in mind the positive side of a mirror is the object side. The negative side is behind the mirror, or the virtual area. 1 over F equals 1 over di plus 1 over do. we're given the focal distance is 15. But we're going to have to put it into the formula as a negative 15 because it is behind the mirror on a convex mirror. So we put that in as a negative 15. We have 1 over di, and then 1 over dou, or the object distance, would be 1 over 40. So we just solve this for d sub I, and don't forget to do the inverse at the end. But you come up with an image distance of negative 10.9 centimeters. And does that make sense if this is negative 10.9? Does that make sense if f is negative 15? Yeah, it's a little bit more than halfway. Now we also wanted to find out what is the magnification of this mirror. So the second formula that I gave you was magnification is negative di over negative dou. So when we put in negative di, remember it's a negative, which is going to make it a positive. So it's the 10.9 divided by the object distance, which was 40. And when we just do the math, we get a magnification of 0.27. In other words, the image is going to be 27% as large as the object.